Hello everybody, it's Mr. Ray here with our next lesson in grade 12 vectors, and we are working in the applications unit for vectors. Today we're going to continue on with the applications unit, and today we're going to talk about the cross product of two vectors. So earlier in the unit we talked about the dot product, and the dot product if you remember, was basically it's the projection of one vector on the other vector, and it's quite useful in determining if two vectors are perpendicular. We looked in the first lesson on dot product, we looked at the geometric representation, and we came up with a formula for the dot product based on the magnitudes of the two vectors and the cosine of the angle between them. In the second vector, we looked at the algebraic approach, where we looked at the components of the two vectors, and there's a quite simple way of coming up with a dot product just by multiplying the x components together, the y components together, and the z components together, and then adding those three products together, and that was the dot product. Okay, so today is the cross product of two vectors. So when we look at the cross product, we use the symbol like a little x, like a multiply symbol. It's important to use the correct symbol, because if you put a dot there, that would imply the dot product. Now, a couple of important things that are different about the cross product compared to the dot product. The first thing is that the cross product is only used in R3. You have to have a three-dimensional representation of the vectors, and the other thing about the cross product is the result is a vector, whereas the result of a dot product was just a scalar, just a number. Okay, now there's something interesting about the cross product, and this is why we use it, is the cross product will actually, if I had these two vectors A and B and I did the cross product of them, it actually gives me a vector that's perpendicular to both vector A and B. Okay, another word for perpendicular, you might see it used in textbooks or on the internet, is orthogonal. Orthogonal and perpendicular mean the same thing. Now, there's something called the right-hand rule, and this is kind of the different version of the right-hand rule. If you obviously use your right hand and you make your index finger, let's see the diagram here. So if you made your index finger vector A, your second finger vector B, and then you kind of aligned the position of A compared to B by flipping your hand upside down, one way or the other, the direction that your thumb points will be the direction of the cross product. And you see there's really only two possible directions. And you also see that going in one direction is A cross B, and going in the other direction is B cross A. So that also tells you that A cross B is not exactly the same as B cross A. So the cross product is not commutative. You can't just change the order. But there is a relationship, which we'll get to in a second. But this will be used, cross product will be used for lots of different applications. And also when we're constructing equations in R3, we'll be using cross product occasionally to come up with new equations. Okay. Now, it also says here that the cross product gives you a magnitude that's equal to the area of the parallelogram that the vectors form. So if you actually extended A plus B and B plus A to form a parallelogram, the magnitude of the cross product gives you the area of that parallelogram. So there's one application right there that can be used. So in terms of key concepts, you can't just assume that they're the same as dot product. We've already seen that commutative property does not exist for cross product. Now there's a formula here to actually calculate the cross product, and you can see that it's based on the 6 components of the 2 vectors, and each vector has 3 components because it's always going to be an R3. You can use this formula if you want. I'm going to show you when we do an example, the kind of using an array of numbers, probably the fastest way to do it. I think most people do it that way. Anyways, here's the official formula. You can see each component. There's 3 components, 1 component, 2, and 3. So that would be the X component, the Y component, the Z component, and you can see it's a subtraction of 2 products of these 6 terms. So we'll talk about how we do that during the example. You can also see that A cross B, we know it's not equal to B cross A, but it's actually the negative. So, and we'll see this in the example, you basically multiply one cross product vector to get multiplied by -1. That will give you the opposite cross product if you reverse the letters for the cross product. Now this property is true. If you do 2 cross products in a row, it actually doesn't matter which. If you do, so if you do A cross B cross C, it doesn't matter whether you do A cross B first and then that result do a cross product with C, or if you did a cross product with B and C first and then did A cross the result of that. So that is a true property of the cross product. So let's look at, it's a pretty short lesson. I just want to do one example of, one example of doing the cross product. So here's another example from the textbook of A cross B and B cross A. So I think the diagram on the first page was a little nicer because it looked more 3-dimensional than this one, but that's kind of a summary of what the cross product is. Okay, so here's our one and only example. We've got 2 vectors, P and Q, and you can see there are 3 vectors because they've got 3 components. It has to be in R3 to do cross product. And we're actually going to calculate both P cross Q and Q cross P. And we kind of know what we should get based on the properties we just saw on the previous page. Okay, so here's how I'm going to show you how to do this. Okay, so if it's P, we're going to start with P cross Q. So the first thing I'm going to do is I'm just going to write the components without the commas, sort of as the top line, -1, 3, 2. And then the second part of the cross product, so in this case Q, 2, -5, 6, I'm going to write that directly below. Okay, and then I'm going to put these lines here to make it look like an array of numbers. And now we'll do our calculation. So P cross Q is equal to, now we know the result of this is a vector, so I'll put it in vector component form. So what we do for the first component, I basically cover the first row because we're doing the first component. And then we basically do kind of a cross multiply here. But so we start off with 3 times 6, and then we subtract 2 times -5, or it doesn't really matter the order we do it. So it's this product minus this product. So when I write that out, I'll do it in the long form. So it's 3 times 6. Maybe I'll use a second pencil so I can keep. So it's 3 times 6. And then you subtract, you always subtract, -5 times 2. And that result, which we'll slowly get to, will be the X component of this cross product. The second component, so if it's the second component, we cover over the second column. And now we do cross multiply again and subtraction, but this time only for the middle one we do the opposite order. So this time we do 2 times 2 minus -1 times 6. And that result is the Y component of the cross product. Third component, you can kind of see what to expect. We cover over the third column, and this time we go back to the same way we did it for the x component. It's -1 times -5, subtract 2 times 3. Okay, and then I put my closing bracket for the vector that I'm creating here. And now I could do this in one step, but let's do it gradually. So that's 18 minus, and so this is actually plus because it's two negative signs, so 18 plus 10, that's going to be my x component. 4 plus 6 is the y component, and that's going to be a 5 and minus 6. So last line, we just add these together. So P cross Q is the vector with components 28, 10, and -1. Okay, so putting them as an array, and you have to put the vectors in the correct order, otherwise you'll get the wrong signs on these. And then for each component, you cover over that column and do a cross multiply, subtract the products. When you do the middle one, so the y component, remember we did the opposite order, so we actually did 2 times 2 first, minus -1 times 6. So that's how you do cross product. Let's try that one more time, but this time we're going to do Q cross P. So what does that mean in terms of what I'm putting here? It just means I'm switching the order of the two rows. So since Q, I might as well write this here, Q cross P. So since Q is the first vector, I put its components on the top line to -5, 6, and P, I put its components -1, 3, and 2, so don't want a comma. Okay, and the numbers will seem familiar because we're basically multiplying and subtracting the same numbers. So again, the first component, cover the first column. It'll be -5 times 2 minus 3 times 6. So -5 times 2 minus 3 times 6. I guess I should keep that second pencil going there. And that's the x component, so -5 times 2 minus 3 times 6. The y component, second component, cover the second column and change the order we do this. So it's going to be -1 times 6 minus 2 times 2. And then the third component, go back to the original order, 2 times 3. Some more room here. 2 times 3 minus -1 times -5. Running right off the page here. Okay, so now we're going to simplify this. So we've got -10 minus 18 as the x component. Then we've got -6 minus 4 as the y component. And then we have 6, and we got triple negative here, so that's going to be 6 minus 5, and that's the end. Then add these up, we get -28, -10, and +1. Okay, and if you compare P cross Q compared to Q cross P, you can see it's like we multiplied one by a scalar of -1 to get the other. Just change the sign of each of the components. Because it's the same vector, just going the opposite direction. If you remember the pictures from the first page, where this is A cross B, this is B cross A. So same direction, same magnitude, sorry, opposite direction, but the same magnitude. And parallel, of course. Okay, so that's how we do cross product. Now, one thing you can do, you can maybe do a little connection back to the dot product. So basically, we know that the cross product of these two vectors P and Q, this is perpendicular to both P and Q. So let's give this a try. Let's actually check to see if that's true for one of them. So I want to see if we did the dot product of P with the cross product of P cross Q, which was our first cross product above. If we do the dot product of those two, we should end up with 0 because they're supposed to be perpendicular to each other. So let's see if that's true. So we already know the components of P, negative 1, 3, 2. And we know the components of P cross Q from here. So we're going to do dot product this time. 28, 10, negative 1. So if you remember how to do dot product, it's just multiplying the x components. So that's negative 28. And we add that to the product of the two y components. So that's plus 30. And add the product of the two z components. That's negative 2. So minus 2. And if we add these together, we get negative 30 plus 30, we get 0. And that's good news because that tells you that P is perpendicular to the cross product that we got. So that result of 0 means they are in fact perpendicular. And if we try the same thing with, instead of P here, we put Q, you'll see that we do get the same thing. And even if we change the order, and if we tried Q cross P, we'd also get a result of 0. So that's a way you can connect how the cross product works and how you can use dot product to check. Okay, so I only did one example. I think once you've seen one, it's mainly just practice you need to try to do this yourself. So I would recommend trying to do this array approach where you cover up the column of the component you're trying to get and do basically your subtraction of the cross multiplications and get your result that way, rather than if you remember the first page, there is a formula here to get the cross product. That is true for sure, but it's not an easy thing to memorize. But I think if you see it more visually like we just did, it becomes more obvious and something you can remember better. Okay, so that's it for today, and I'll see you in the next lesson. Take care.